You are most welcome to Technical Pathfinder, the Learning Center. This is the PSU quiz series for BTech electrical engineers, and we are discussing some more problems so that it can help you in upcoming exams. Here the first question is, the fault having equal sequence voltages at the fault point is 3-phase, double L, double LG fault or LG fault. The answer is double LG fault. Next is numerical based problem. A 100 MVA 11 kV alternator have three sequence reactance positive, negative and 0 as 0.3, 0.4 and 0.5 per unit respectively. He is asking the resistance at generator neutral connected so that the fault current for LG fault of zero sequence impedance will not exceed the rated line current. So it should be less than 1 per unit fault current. We have fault current formula is 3 by x1, x2, x0 addition with 3Zn, and fault impedance is 0 here. And Zn is given as resistance at connected at neutral side, and EMF is given 1 per unit. We can find from here the neutral resistance, and after finding the neutral resistance in per unit, we will convert it to the ohms by multiplying it with the base impedance, and base impedance is equal to kV square by MVA. So the answer is 11.71. In next problem, per unit values for positive, negative, zero sequence reactance is given, and he is asking the fault current for double line to ground fault. So this is the double line to ground fault sequence diagram, and according to this we can find IR1, which is equal to 1 per unit is the voltage divided by total impedance is 0.14 and 0.1 is parallel, and after parallel combination we will add the impedance to 0.16. So IR1 is 4.58 per unit, and fault current will be equal to 3 into IR1. Answer is 13.74. Option B is correct. In the next problem, two power station P and Q having short circuit capacities 800 and 600 MVA respectively operate at 11 kV each. Let the base MVA is 100 MVA and base kV is 11 kV. If the interconnected by a cable 0.4 ohm reactance per phase, then maximum short circuit MVA will be. So we will find the per unit reactances for station P and Q by dividing the base MVA to their short circuit capacities. So it is 0.125 for P station and 0.166 for station Q, and the reactance connected is 0.2 ohm, which is in reactance ohm per phase. So we will convert it into per unit by dividing the base impedance, which is equal to 1.21. So it is 0.33. After connecting this, we will see that 0.125 and 0.33 in series. After this combination, 0.166 is connected in parallel with the two. The reactance of the total circuit is 0.1216 in per unit. After dividing it to the base MVA, we will get the short circuit capacity of total system. It is equal to 819.67 MVA. In next question, 3-phase 10 MVA 11 kV alternator have sub-transient reactances 8%. The 3-phase short circuit occur at terminals. Fault MVA will be, so fault MVA equal to base MVA 10 divided by per unit reactance is 0.08 MVA is equal to 125 MVA. It is equal to the fault MVA, and fault current will be fault MVA divided by root 3 into the base kV. It is 11 kV, so it will be in kiloampere. Answer is 6.56 kiloampere. Option B is correct. In next problem, 500 MVA 20 kV 60 Hz synchronous generator have direct axis sub-transient reactances 0.2 per unit, supplying purely resistive load of 400 megawatt at 20 kV. Load connected directly across the terminal of the generator. If all three phases are short circuit, then symmetrical RMS current in per unit will be, so three phase current is EMF divided by per unit reactance, and EMF will be found by terminal voltage plus J into Ix, and current can be determined from 400 megawatt is given, and the capacity is 500 MVA, so 400 divided by 500, because the voltage is same, so the current is 0.8. So 1 plus J 0.8 in per unit multiplied by the reactance in per unit is 0.2. It is given the subtransient reactance is 0.2. So the EMF is 1.0127 per unit. If we will put in this formula, 1.0127 divided by 0.2, answer is 5.006 per unit is the three phase short circuit fault current. In next problem, three phase generator is given with their rating and three reactants are given, but to find the initial symmetrical RMS current we need only subtransient reactance. So initial symmetrical RMS current in the breakers will be 1 divided by reactance, it is 0.19, multiplied by total MVA is 110 divided by root 3 into kilovolt is 11, it will be in kilo ampere. So this is the symmetrical RMS current in per unit, and we will multiply it by the actual current, we will get the base current, we will get the actual value 30.39 kilo ampere. A 50 Hz alternator rated at 500 MVA 20 kV with the two reactances XT and XT double dash supplied purely resistive load at 400 megawatt at 220 kV. Load connected directly across the generator terminal when symmetrical fault occur at load terminals. The initial RMS current will be, so EMF will equal to 1 plus G 0.2 multiplied by 1. 0.2 is reactance, it is subtransient reactance because we have to find the symmetrical current, and 1 is the current per unit. So magnitude of EMF is equal to 1.04. Per unit current will be equal to, fault current is 1.04 divided by 0.166. 0.166 is equal to the 1 parallel with 0.2. So the two reactants come in parallel, we get 0.166. So the current per unit is equal to 6.25. Option B is correct. In next question, and for an unbalanced fault with paths for zero sequence current at the point of fault, what will happen? Negative, zero voltages are minimum? No. Negative and zero sequence voltages are maximum. So it is the correct answer. For a unbalanced fault, the path for, if there is a path for zero sequence currents, so at the point of fault the negative and zero sequence voltages are maximum. Option B is correct. And the last question is, for a fault at terminal of synchronous generator, the fault current is maximum for LG fault. So we know that it is the highest severe fault. That's all in this session. Stay connected for more videos and keep practicing.